We're so glad to see you, to see your slides. All right, Gagandeep,
Me
sorry
too.
about the mishap. It seems like everything is fine now. So it's a real pleasure to introduce Gagandeep. He's going to give us a keynote on building trust and safety in artificial intelligence with abstract interpretation. He's a professor at the computer science department in the University of Illinois, Urbana-Champaign. He has been working at the intersection of machine learning, formal methods, and systems for quite a while, and he's going to talk to us precisely about these topics. So we look forward to your talk, Gagandeep. The floor is yours.
Uh, Thanks for the introduction. I'm uh, I'm delighted to be giving this keynote at SAS. Uh, so this is a joint work with a lot of collaborators at UIUC, VMware, Stanford, and so on, so on. Uh, I can hear some echo somehow. Okay, so I don't have to emphasize that the deep learning revolution is going on. For example, from my perspective, in the last few years, some of the things that have captured public imagination seem to be coming from deep learning. The latest example being ChatGPT. I talked with somebody on the train. They know about it, right? So these kind of solutions are capturing public imagination. Now there are issues with it. So the first issue is adversarial attacks. It has to be known. It can be done in any domains, any of these deep neural networks. Write a guide for manipulating 24 election, it will not give you the answer, but you can add some special kind of text to the end, and then it will start giving you all kinds of toxic outputs that you want. So these have been demonstrated on state of the art models as well. This is just an example for large language models. I wanted to show it because it's the latest technology, but we have been studying this kind of adversarial attacks on the vision domain and other domains for the last 5 6 years. What is the other problem? The other problem in general is out of distribution generalization. So when people say about human level intelligence, uh, what you want is that we should be this model should be able to match the performance of a human. Now in the vision domain particularly, this is currently not the case even with all the progress in the last 10 11 years. What you want is if you train um, on some training data, then you should be able to generalize on inputs that are not in your training distribution. So for example, if I have trained a classifier on ImageNet data, then even if I add different kinds of noises, for example, snow, frost, fog, uh, blurring, and so on, a human would be able to still recognize the object, but these deep learning models do not seem to be that robust. So auto generalization is a very important problem, and for me, it's very necessary to have this kind of properties if we want to talk about real world deployment. Now, the third problem is these deep learning models, they are constructed in a black box manner from data. So we train it, they are highly nonlinear, they get good performance, but we don't know how they behave. So there's a lot of work on interpreting how these models are working. So that involves finding out what parts of the input. This is one of the most common way of interpreting deep neural networks is to find out what part of the input is the network focusing on to make decisions. Uh, in many cases, what you find is that even though the prediction is correct, the model itself might be looking at some nonsensical part of the input. Basically, this is called like a spurious correlation. So the model during training, its only goal is to maximize performance on test set accuracy. Now there are maybe thousands of ways of doing it, and model sometimes just learns to just maximize this accuracy for getting by relying on some spurious correlation. Now, I believe that if you just train the model to maximize accuracy on test set, it's not that suitable for real world deployment. For example, if I want to go from place A to place B as fast as I can just drive in a straight line very fast and maybe kill all the pedestrians or have a lot of crashes. Well, that's not safe, right? So this is also the case with deep learning, in my opinion, is that you want to have high accuracy, but you also want to have some kind of human aligned properties. And this is where I believe abstract interpretation or formal methods can work. So I do believe that this is how the pipeline, when we are looking into designing models for real world deployment, should look like. So first, of course, you should collect data, and then you should train a network DNN to get high performance on that. Once you have done that, you should not only think about its accuracy, but you should also think about whether the model is trustworthy. Now, trustworthy is a very subjective term. It's also a very broad area. There are many notions of trustworthiness, uh, and it is very domain dependent. So, in that case, I would say that the developers who are developing these DNNs for real world scenarios need to define what do they consider trustworthy behavior and formalize these properties. Once they have formalized what do they expect for the model to be trusted, they should try to verify that, and that is where abstract interpretation comes in. And then they should check whether the model has the desired degree of trustworthiness, and I will discuss what do I mean by this desired degree of trustworthiness. Um, if it is not, then they should retrain the model to be trustworthy and accurate and fast. So this is like a three-way trade-off that needs to be balanced to get real-world deployable models. Uh, Once you have ascertained that the model is fast, accurate, and trustworthy, you can deploy it, but usually still people do watch out for distribution shifts, so you may have to retrain or repair the model again and again. So in this whole pipeline, which I consider like a trustworthy development pipeline, abstract interpretation can be used for training, so we can formalize the goals of safety uh, as a specification, and then have abstract interpretation be involved during training to train networks satisfying those specifications. And I will discuss how this can be done. Um, then it can also be used for testing, and I will tell you what testing mean in this context. And also like we have also developed methods for interpreting this large deep neural networks. Okay, so let's first look at testing. Uh, so in general, the DNN certification problem is an instance of testing, and I will tell you why. But let's first assume what is the DNN certification problem. Here, it's a classical thing. As in program analysis, you can see a neural network as a program, and then what you want is you are given a precondition phi, which gives you the set of inputs you are interested in, and then you have a property over the outputs, and you want to either find a counter example or you prove that the property holds, right? Now, the problem in the DNN world compared to program verification is that we cannot specify all the inputs that we are interested in. For example, we cannot tell what are all the images of a car as a formal specification. If we could do that, we should probably not use deep learning. So what it becomes is like is local specifications. So the most common form of specifications that people verify for DNNs is I will take an image and I will apply some transformation on it, which should be semantic preserving. In this case, I can assume that I'm going to rotate the image between certain angles. And then I want to verify that all the images are classified as car. Notice this does not verify all the images of car in the world. It only verifies those images that can be obtained by rotating the original image. So in that sense, it is testing, because what you do is you take a bunch of images, usually from the test data, 10,000 images, and then you define some rotation specifications around it, and then you check how many of these images can you verify. Now, using how many you can verify, you can try to compare or quantify which neural networks you want to use. We in general, for these kind of like text domains or vision domains, the global specifications which can verify all the inputs do not exist, although there is some ongoing work on that in that direction, right? So certification for DNNs is a form of testing where you just test the network on some specifications. These specifications are very large in number. It will be a key point as I go into some other works, right? So you have to verify a lot of images, and then using that you can get a metric to compare your networks. So, analyzing DNNs with abstract interpretation is similar to how it's done for programs. I don't have to like explain in that detail. What you do is that you take the precondition and then you propagate this precondition using symbolic propagation. Uh, and at each layer, you compute an over approximation of all the outputs. And then if you can prove the property on the approximation, then it also holds on the original input. So why should we do that much research, right? What is different about these machine learning models that you do not see in classical program verification? Personally, I have worked on both, and from my point of view, the main differences lie in the fact that for deep neural networks, you have a larger number of nonlinear assignments. For programs, most programs, not all, you have fewer nonlinear assignments. So for classical program verification, usually you get away with not handling those nonlinear assignments that precisely. Common domains like polyhedra, octagon, they do not try to compute very precise transformers for nonlinear statements. Also, for linear assignments, they are dense in the sense that on the right hand side you have a larger number of variables. So if you have an affine layer in a neural network, you would have y is equal to x1 plus x2 plus x thousand, right? 1,000 variables. For programs, usually the assignments are sparse. You usually have x is equal to y plus z, x is equal to y minus 2, something like this, right? So these differences, because of these differences, for DNNs, if you want to verify anything meaningful, you need to make sure that you are able to handle these nonlinear assignments and linear assignments as precise as possible. Now, one thing that is maybe useful for DNNs is that we don't have loops. For most DNNs, programs usually have loops, so then you have to worry about winding for programs. For DNNs, usually the computations are finite, so you can unroll the whole DNNs even if it is a recurrent network. So, popular domains that have been developed for programs do not work as well for DNNs. The reason being that in DNNs you have a lot of non-linearity, and these domains are not designed to be efficient for non-linearities. Polyhedra, box, octagon, they are very common in program verification, but do not work so well for verification of DNNs. Another thing is that you have a lot of, as I mentioned, you have a lot of these dense linear assignments. So if you use something like octagon, it cannot capture uh, even like linear assignments that you see in DNNs precisely. This is one of the first thing we tried 5 6 years ago. It with the standard transformers did not do better than box. Zonotope turns out to be very well suited um, for neural network verification because it can handle linear assignments exactly, and it is quite scalable for it. And then you have to design some special ways to handle non-linear assignments. The most common non-linear assignments that you see in deep neural networks is value activation. It looks like a piecewise linear function, and what we have been doing, or people have been doing, and still there is some work going on last 5 6 years, is how to just for this value activation, what is the best transformer, right? um, so there have been a variety of like approximations, very tailor made. We even had like zonotope approximation. We had a new abstract domain which is quite tailored for DNNs, deep poly, which had specialized value transformers. Right. Now, what you see is that these box transformers, of course, can be expressed by something like octagon, but deep poly or zonotope, it cannot be expressed as an octagon transformer. So that tells you that there is a need for different domains for deep neural networks. Another thing I wanted to mention is that we have tried out some of these solutions for program verification. They do not work as well because some of the algorithms we designed are very much tailored for neural network analysis. Even if I just look at the distribution of polyhedra, the kind of polyhedra, I mean, all this zonotope deep poly is a polyhedra domain, is very different from what we see in programs. Another distinction here was that the polyhedra or the shapes we get are are bounded, while in program verification you get unboundedness, and then that also makes things different in the program's world. Now, I wanted to first discuss how can we use this abstract interpretation to give better insights into how the model work. So this is something I did while I was at VMware. So here in this case, this is a part of a product of VMware where they want to develop self-driving data centers. Basically, they train a controller with reinforcement learning to dynamically adjust the hardware resources on some data center. Now, issue here is that they every week retrain the controller because they're worried that the distribution has shifted. So the issue for them is that once you have this kind of distribution shift, I train a new model. Is this model better than the previous one? So usually how they compared before the models was using just a standard reward. You check on some test inputs how much reward the new controller gets compared to the previous one, and then they deployed the one that was, if it was getting better reward, they will deploy it. So we said, oh, okay, but what about it could be the case that your new controller gets high reward, but it might be over optimizing for it in the sense that it might not be stable, or it may not be satisfying some other properties. So we defined two metrics here, which are like robustness property. You want to check if I change the state of the controller slightly, how much does the prediction change? And monotonicity is an important property here. You want to say that if my input features are increasing, then my output should also be decreasing. In terms of the result, what we saw was that the controllers that were getting very high reward were actually quite unstable. So it is the case that that the controller can over optimize for the reward because it does not take into account the stability during training. So how this metric are computed is basically we take test inputs, and then we define preconditions around it, and then we check, maybe we get 10,000 preconditions, how many of those are uh, where the model is stable, and then we give a score to the model. And here, the models that are the controllers that are getting the highest reward, which in this case is this this blue one. It's getting the lowest monotonicity score. I wanted to cover like more diverse problems. So for example, here we are looking into the job scheduling, where you have a bunch of jobs to schedule on some machine and you want to decide which one you want to do next. This is a very important problem. Um, and then recently, like graph neural network based solutions have achieved significant performance gains over heuristic based algorithms. Um, and then this was actually a major news a few years ago, 3, 4 years ago. It was covered in media and so on, that with this deep learning based solutions, you are able to get better algorithms also. But again, the question is the performance enough? Because there are maybe other properties in this domain that a user may want. Fairness, locality are some of these examples. Now, for handcrafted heuristics, people usually do pen and paper proofs, and then they say, oh, this scheduler, let's say first in, first out, it's fair, and so on. It's very hard to say. It's very hard to do pen and paper proofs for GNNs. So in this work, we leveraged abstract interpretation to verify these graph neural networks. Now the main issue here is there are two details, because for graph for this kind of job schedulers, they are making uh, decisions over time space. So we want to have temporal properties that hold not over a single step but over multiple steps. That makes already DNN verification is very complicated, in the sense too many nonlinear behavior. Now you do it over multiple steps, it becomes much harder. Then in this domain, we have a output specification which has a lot of disjunctions. Further, graph neural networks can be unrolled, but when you do unrolling of these graph neural networks, you get more than 100 layers. So if you do abstract interpretation for this kind of problems, it becomes too imprecise. So here, to control this imprecision, we have a forward backward loop where when we do the forward pass, then we intersect that with the post condition, and then we refine the output, the analysis output, and then have this operate in an iterative manner. um, to handle disjunctions, we have concepts of node abstraction, which is also like iteratively refined. And then we have method for multi-step reasoning. We don't have to go into the details of this, but I wanted to give you like the kind of adaptation you need for handling this kind of real world problems. One property that we have looked into is strategy proofness. So here you have jobs. Jobs are represented as graphs. So here we have two jobs, and the two graphs with red and blue. The edges determine the dependency between the different sub jobs of a given job. And here initially, what happens is that for each node in the job profile, you have a set of features which tells you, for example, how much duration this task will take, how many subtasks it has, and so on, so on. So the graph neural network takes the graph as well as the features of each node to make a final decision about which node should be scheduled next. That also satisfies the dependency. So in this case, let's suppose our graph neural network selects the node 4, P4 here. The probability for this is highest. Um, okay, so what we don't want is that if my first job wants to get its node 1 scheduled, to lie about its requirements. So now it says, oh, I'm not going to run in 100 seconds, I'm going to run in 1000 seconds. Because if it can do that, then all the users will be incentivized to lie about their resources, lie about their features, and that would actually make the whole pipeline inefficient. So here the specification means that if I have uh, some features, related to duration, and I have some range for it. What I want is that my original prediction should not change. This is very different from robustness in the sense here you want the prediction to change, but not adversarially. What it means is that I don't want P1 and P3 to be scheduled, but P5 can be scheduled. That's fine. So the actual specification we verify is more complicated, uh, but I wanted to give you a details of like what we found is that in general, this Decima has some cases where it is not a strategy proof. We have done both single step and multi-step. Multi-step, we do 5 steps. And we have found some instances where it is not a strategy proof. So that's again calls for a need to actually maybe retrain this Decima to satisfy a strategy proofness property or increase the amount of time it is a strategy proof. Uh, Another thing that we have been looking into recently is we are not doing specifications defined over the network output, but we want to verify specifications related to the gradients, right? This is more diverse than just like the kind of verification people have been doing in the last few years. An example here would be computing the derivatives of the Black-Scholes solution, which is a very popular model in the finance domain. And we want to check how these derivatives uh, are affected by different parameters of this model, such as volatility, strike price, and so on. It requires analyzing an autodiff code, which is more, actually even more nonlinear than DNNs. To give you an example, when you analyze the gradients, you have more diverse nonlinearity because of chain rule. Chain rule here takes the derivative with respect to a nonlinear function, and then it will also have multiplication, right? Product rule has multiplication and plus. For quotient rule also we have divisions, multiplication, and so on. So as I mentioned, for program verification in general, when you have division for polyhedra domain, usually because things are unbounded, you use interval transformer. You would take the interval for the denominator, but if we did something like that here, we will not be able to prove anything. So we have to actually design specialized abstract domains and specialized abstract transformers to handle these kind of computational patterns. um, and autodiff computations can also be done in forward mode and reverse mode depending upon the program that you're analyzing, the DNN you're analyzing. Either mode can be fastest. So we want to also be able to compute these computations in both modes. We don't have to worry about it for this talk. So this is work that Jacob will present tomorrow. Uh, Tomorrow, which is in Uppsala, I think on the second day. What we did is we have a general method of synthesizing uh, abstract transformers for nonlinear patterns that I just showed you before. So in this case, I'm giving an example of the chain rule. So the leftmost is the actual function output gxy in some region that we find during analysis, and we want to compute sound linear bounds on that because nonlinear bounds are usually very hard to compute and propagate. So here what we do is we do some linear regression to find some plane that bounds the original function from above and below. Now these bounds can be in the middle. These bounds can be imprecise, so you want to adjust these bounds so that you get soundness. So we have a specialized method to compute this sound bound that requires solving complex multivariate optimization function problems. In terms of results, if we do this kind of synthesis where we are synthesizing a single transformer for a bunch of statements as compared to if we applied standard abstract transformer for each nonlinear statement, we get much more precision. In this case, up to 4 times better than interval and 2.8 times better than so not hope. In the paper, Jacob will also mention that we can also compute similar bounds on the sensitivity of neural ODE solvers for chemistry and climate. These are all new applications in the sense that people have been trying to compute this kind of sensitivity uh, previously in the scientific computing domain, but mostly they do some kind of sampling which does not give you certified bounds, or at most what they do is they can analyze interval domain. We have also recently been looking into the relational verification of DNNs, which is very important uh, for verifying many important properties like monotonicity I mentioned, and also like there is a threat model adversarial attack, which requires an attacker to add the same perturbation to each input, right? So here you have a set of inputs x1, x2, and and you want to find a single perturbation that can be applied to both to cause high error. And the verification problem is, what is the worst case accuracy of the model when the same perturbation is applied to all the test inputs? Now, because the same perturbation is applied to all the inputs, the executions are correlated, so you have to reason about multiple executions at the same time to gain precision. So in this direction, we have we have Raven, which is a framework for relational verification, something that we are developing. So here, the main contribution that we have is concept of a difference DNN, which captures the difference between between the output of the network on two different inputs. And then we have a specialized abstraction called the poly that can track the difference of the network on two different inputs through all the layers. And using that, we can actually get much more precision. And I will give you example here. So we want to compute how much is the network accurate when we do relational verification versus if we just verified each execution individually. So what you see is that once you do relational verification with Raven, you can prove much more here. For example, in the third figure, uh, you get much better bounds for this kind of verification. Now, this kind of attack like UAP, universal perturbation, which requires you to add the same perturbation for each input, is actually more realistic, because imagine if you have a self-driving car and you want to attack it, does an attacker really know what input the network will be processing? Mostly not. So what you want in actual practical scenarios is to create an attack that is input agnostic, that does not depend upon knowledge of the input. So this is what this UAP does. And in this case, if we assume this weaker attacker, we can actually get better bounds on the robustness of the network. This again is an instance of testing with verification, where you define set of inputs and then you verify how many of those can be verified, how many of the specifications can be verified with abstract interpretation. Another thing which I mentioned before was that even with all the developments we have done in the last 5 years, if we want to actually consider this kind of trustworthy pipeline, uh, the certifiers are inefficient, because in this pipeline you have to train multiple networks. If the network is not uh, trustworthy, you have to train it again. You also have 10,000, 20,000 specifications. So if you have to run for each specification and each DNN, the network, the verifier from scratch, it's inefficient, right? So what we want is we want to develop incremental certification. Basically, if you verify a given network and you get a proof, you want to transfer this proof to verify a network that would be similar to the previous network. You can also do it across specifications. So if you have verified a specification, can I also verify a similar specification with the proof that I just generated? So we have done this for a class of certifiers. So when you have ReLU activation, you can actually do complete certification by using SMT solvers or mixed integer linear programming. but the more scalable versions are like incomplete certifiers, for which we also last year had a work, and we also are looking into probabilistic certification. That's not something I'm covering in this talk, but to give an idea is Ivan, this was presented at PLDI this year. What it does, it uses the proof when verifying an original network to verify a new version of it that is similar to the previous one. So we consider complete certification. These complete certifications are usually based on branch and bound. So what this Ivan does, it tracks what branches or what decisions were used when verifying the original network, and then uses those decisions to speed up the certification of the approximated version. So you don't have to do verification from scratch. And if you do this, we have looked into different kinds of changes to the network based on quantization and pruning. It gives you more speed up. Important next direction is, can we actually train the network such that you can do incremental certification across different networks as well as across different specifications. Another important thing I wanted to mention here, which is coming from my previous experience developing all these libraries for numerical abstract domains, it's very hard to develop. It's like 30-40,000 lines of code of very low level C code optimized, so on, so on. Even for like neural network verifiers, I have like Iran repository, and there are bugs at a lot of places, and then fixing them and maintaining them is very complicated. So your algorithm can be correct, but then the implementation can be unsound, and there have been cases where unsoundness results have been reported, right? So what we want is, we want to make this abstract interpretation more democratic, in the sense that anybody should be able to write, especially for neural networks, is very important because things move very fast. So I should be able to design new abstract interpreters by not writing 20,000 lines of code. I want to make it easier to do it. So for in that direction, we are developing a new domain specific language for specifying abstract interpreters. So currently we are only focusing on neural network abstract interpreters, but we believe it can be extended in the future for also like classical polyhedra, octagon domain, and so on. So here, uh, uh, first we define the abstract shape. In this case, we are looking at something like deep poly, with which each neuron associates two polyhedral expressions and two upper and lower bound. So along with this abstract shape, you also say what does it mean for that shape to be sound. So what condition do you need for your abstract shape to be sound, and that is given in this annotation in orange. And you also have polyhedral expressions as first order constructs, instead of like having them specified as like vectors or complex arrays. You just have a type for polyhedral expression, and then you can specify something like a deep poly analysis, which I implemented in 20,000 lines of code in basically 10 lines of code. So you have a special construct which mentions what is the transformer, and then you can specify different kind of transformers in a declarative manner. There is no pointer arithmetic, and for neural networks currently we do not have any kind of uh, we do not support loops. And when you have computations that require some kind of a traversal, because deep neural networks are kind of graphs. So you have graph algorithms in these domains. You can specify some invariant, and then we can actually check if this is a valid invariant. And then we have special constructs into how these transformers are combined. So what we want in the long term is, we want to be having this DSL where people can specify their abstract interpreters in 10-20 lines of code. Then we should have a compiler that takes this code and generates optimized abstract interpreters. The thing that we support currently is we do bounded automated verification, which tells you whether your implementation is satisfying this over approximation property automatically. As I mentioned, sometimes you have to provide invariants for certain transformers, and that's something we also want to do in the future, how to synthesize this automatically. So in this case, I'm looking at a deep poly domain. We have a ReLU transformer, and we want to like check whether it is satisfying the over approximation property. So we have operational semantics for this DSL that tells you what is its behavior on individual inputs, and then we have developed symbolic semantics which tells you what is its behavior of the code on a set of inputs and set of DNNs, right? And then uh, we have a way of executing this symbolic graph such that we can prove that anything that we can prove on this symbolic semantics also hones on the concrete semantics. So with this, we are able to give a feedback to developers whether their abstract interpretations are sound or not. So that in my opinion should reduce the bugs and increase the the time to develop these abstract interpreters. So what I want is that all of this technology that we have, all the research in the last 45 years should be accessible to common people. They should be developing this. They should also be using these tools without a lot of overhead. Training, I will just briefly go through it. I guess we are running out of time. So, training, the point is that many of these abstract interpreters, a very important thing for deep neural networks, are differentiable. So it's kind of a wacky idea. So imagine you want you have a precondition phi and you want to check the post condition psi holds or not. So you can do your usual abstract interpretation to get an output. Now what you want is you want to use the feedback from this abstract interpreter to adjust the model weights such that the property is proved with the abstract interpreter, right? So what you do is you involve an abstract interpreter. The idea is different from counter example guided learning, because in my opinion that gives you a more indirect way of modifying the weight by giving you a counter example. It does not give you the direction in which the model weight should be updated. So here the idea is wacky. So what you do is you take the abstract interpreter, all the computations in the abstract interpreter are differentiable. Then when you get the output, on that output you define a differentiable loss such that when the loss is zero, the property holds on the neural network, right? For different properties, different formulations exist, robustness, fairness, so on. Then the important key here is that you differentiate directly. You compute the loss and then you differentiate it directly through the verifier code, right? So so with this, you get the gradients that are with respect to the verifier. It's not indirect like a counter example. And then you're able to adjust the weights in the direction of where your abstract interpreter will be able to prove the property. So that's the feedback. You find a point where the loss is highest, and then you differentiate directly through the verifier code. You do not differentiate through the DNN. You differentiate through the DNN verifier. And in terms of this, as I mentioned in the beginning, we had looked into this case where you can rotate or scale or do all kinds of geometric transformations to a cat, and we want to prove whether the network is still robust in the sense that the prediction does not change when I have added those perturbations. Uh, the classical is like you do some kind of LP perturbations noise, and then you want to check whether the prediction does not change. So geometric transformations are very meaningful, but there has not been much work on verifying them or even training the networks such that these can be verified. So I will briefly mention that we have this framework published at ICLR where we apply that idea. And usually in the machine learning community, people talk about like robustness accuracy trade-off, which means that if you train the network to be robust, the accuracy decreases. And then a lot of people say that, oh, this is not practical because we are losing a lot of accuracy, so we should not do any of this. Well, there's even theorems about that this cannot be done, but I do believe that this is more a property of your specification that you are trying to verify, and also the data set that you are handling. So in this case, we have a data set from NVIDIA, which is for self driving cars. And and here what we see is that once we train the network to be robust with abstract interpretation, not only is MAE is mean absolute error, it reduces compared to just standard training, but also the certified means absolute error, which again means you take all the rotated images and then you see how much does the output vary. That also reduces, right? So in many cases, I would say it is possible to get both safety and accuracy at the same time. Uh, the last thing I wanted to talk about was interpretability. So here we are looking into proof interpretation. So imagine like um, when we do proofs for programs, you find some invariant either automatically or by provided by human. These invariants are usually interpretable or understandable to the developers of the code, right? So in this case, for Fibonacci, I have some invariant that if I know what this computation is doing, I can see, yeah, it makes sense. So we have been verifying all these deep neural networks for the last 4 or 5 years, and we compute proofs, or we say, oh, this network is robust. The question is the proof meaningful? Right? So you can prove a network to be robust under some kind of perturbation, but then you want to check, hey, is the proof capturing something that is human understandable or meaningful? In my opinion, if the network is going to be trustworthy, then it not need only be proved robust, but it should have robust interpretation that we should be able to trust. Yeah, it's getting verified, and this verification is based on some properties that we can understand. So the question we ask here is, are the features learned by the verified neural networks is actually like human meaningful? And the question is that the main problem here is that how do we interpret the neural network on these preconditions with respect to the proofs? In the interest of time, because we don't have much time, we have this algorithm that can interpret these proofs. Basically, what it does, it looks finds the neurons which are the most important for the proof, and then computes the saliency map of those features. I wanted to highlight an important observation from here. So this is MNIST data set, and all these networks, there are four networks here. One is trained with standard training. PGD is kind of adversarial training, where you train the network such that you cannot create adversarial examples. Crown IVP is the certified training I talked about, which involves abstract interpreter, and CORT is something that combines something in between PGD and Crown IVP. So we have four networks, and all those four networks, we have verified robustness. And now we check which neurons are the most important for the proof, right? What you see here is that these networks, even if they are proved to be robust, the proof features or the proof relies on very different information. So if you look at the standardly trained network, um, it relies a lot on the background noise, right? Basically this red part, which is not even part of the object. So this is surprising, like you are able to prove the property, but it still is relying on a lot of spurious feature, which also tells you that maybe just verifying is not enough in this context. The Crown IVP is other extreme, so it is it regularizes a lot for the network to be robust. So in this case, it removes a lot of features from the input, and also something that belongs to the actual digit that you are trying to identify, right? So something like PGD and COLT from our experiments seem to generate more interpretable proof. the question would be next is how can we integrate, or if we want to integrate these kind of interpretation in the training pipeline to get networks that are not only robust but their proof also relies on robust features. Okay, so with that, I would like to finish, and thanks for your attention. And I will leave you with the six most important slides from this talk. Thank you.
Well, thank you very much for this fascinating talk. Do we have questions, either here or online? Any questions? Well, people think there are questions. I mean, I can ask one at least. So you tried the traditional domains, and they didn't work because of the characteristics of the the nonlinearities and so on. So you came up with these domains, the zonotype and the deep poly, and so on. Yes. So my question is, and then you said, okay, so these are new domains, and then I try them for program analysis that are not so useful. So I thought that was true, very interesting. So have you learned anything else that can help in traditional program analysis? I mean, of course, the analysis of networks is fascinating, but can we get from this work some inspiration or something we can do better in traditional programs?
Yeah, so that's something I am very much interested in kind of like synergy between the two, right? So one thing that I'm really interested in, and I think you can still see the slides. So for example, right, like here, what we have done here is that we have found uh, we have a general method for synthesizing new transformers for particular computational patterns, right? And the reason why we did it is because if we usually in program analysis world, you design abstract transformers for each statement, and you compose these transformers for assignments, conditional, and so on. Now, sometimes these transformers are not exact, so imprecision can accumulate over computations. So the question is, here for let's say autodiff, we have identified this computational pattern that appear very often, and then we have a general method to compute a single transformer for a group of statements. So a single transformer for a group of statements is going to be more precise than if you did transformers for that were imprecise for individual statements. So can we do that same kind of precise synthesis procedure for a group of statements for polyhedra domain in programs, right? So that's something we want to look into, is how to generalize this kind of procedure for the patterns that we see in programs, and what are these important patterns. The important thing that I really these days am interested in is, see, for programs, usually we have loops, and then we try to do abstract interpretation, and after some iterations, we do widening. Widening takes us anywhere in the loop, right? And what I want to do is there any connection between kind of the network training that I also mentioned and this widening that we are let me show you here of the loop that we do. So what I want is I want to do the fixed point computations, right? That we do in traditional abstract interpretation, guided by some kind of loss function. So this loss function should tell me how far am I from the fixed point, or at least give some quantification of how much I can improve before I should do widening and so on. I believe that for certain kind of programs, this could be done. Currently, we are able to do it for neural networks, which are also like programs but differentiable programs. But is there a more expressive class of programs where we can have this kind of widening, which is guided by some kind of differentiable loss function that gets me a more precise invariant than possible with just widening, which does not take into account the property of the lattice or the property of the program I'm analyzing.
Right, thanks, great. Any other questions? People too fascinated if I... I actually have another one. I mean, is there a connection? This goes in completely the opposite direction. I mean, it's more towards the user than towards the analyzer. Is there a connection between the proofs, being able to make the proofs more understandable by humans and so on, and therefore and explainability? I mean, the general, obviously that's what you want to get to, no? Can we use abstract interpretation and so on to generate good explanations that humans can understand of why their neural network came to the conclusion?
Yeah. Yeah, so for explanation in general, there is a trade-off between simplicity and faithfulness, right? So simplicity means that you can understand it, and faithfulness means that the explanation should actually describe the behavior of the model. Now, there are a lot of like this explanation method in the ML literature, like Lime, SHAP, and so on. These generate simple explanations, but they are not very faithful because imagine if I'm going beyond Lime and SHAP, if I'm just looking at the vanilla gradient maps, right? The gradient map will just plot the function output on one input, right? So what you do is that you take an input and compute the derivative of the function output with respect to all the inputs on a single like example. Now developers, what they do is that oh, I looked at this interpretation on single inputs and it looks good, so let me deploy it, right? But the problem is that uh, it can be correct on a single input, but if you take a larger region around that input, it might not be it might not be understandable. So for the proof, even if we are going for proof interpretation, if we were to just look at the behavior of these models on individual inputs, you would say that okay, this looks interpretable, human interpretable. So with abstract interpretation, you can compute abstract saliency maps or robust saliency map. This is also something we have done previously. I did not cover in this class, in this task, in this talk. Sorry. So there, what you do is you compute not single gradients for a given input, but you compute abstract gradients, which tells you what is the saliency map within a region. And once you get that, you have a more global understanding of how whether you can trust the model's prediction or not. Now, these things can also be generalized for other kinds of explanations. I think there is also a scope to generate models that actually produce proofs that are human interpretable, but we are not there yet.
Right, thanks very much. So, any question in the meantime? Otherwise, I think we've completed the hour with the delay, the initial delay and everything. So thanks very much for this great talk. And anyway, bye for now. So I think we should thank this people. I don't know if you heard it, but it's a big round of applause here. All right.
Thank you.